Just one short minute. I will just grab Alexey from the front so he can have his first talk, because I think we are everyone here. So just 1 minute. Yeah. So you have like one minute for because I will introduce you. So
me. Okay.
Yeah. No, you can stay. So good morning, everyone. So happy you all made it this morning. So I think it was a late evening, early morning. So I still hope you're fit for the last batch of Quantum for today. And we start with the paper session, the second part, and yeah, maybe some one or two organizational stuff for the beginning. So please keep in mind at 10 a.m. Or 10:15, we will start with the groups for the quantum computer visit. Yeah, basically we will do this in batches. You see, as a reminder, the batches at the front at the registration, you find all the groups. Yeah, we will guide you to the quantum computer and back. And yeah, the talk will, the presentation, the quantum computer will approximately take 20 minutes plus 20 minutes walk to and back from the university. And yeah, I hope you will enjoy that. And yeah, one last bit of organizational stuff. Once you leave, when you go out, there is on the left hand, there is a large table, a higher table. Please drop your badges there so we can recycle the yeah, plastic stuff. Okay. And without further ado, I would like to introduce the first speaker for this session, which is Alexey. And he will present 3 technologies to solve discrete optimization problems with quantum computing. And with that, the stage is yours. So this is presenter, and yeah, sure. You have the.
So this is forward. Okay.
Yeah.
Yep. Thank you so much. Yeah. So that's supposed to be a hands-on work. So this is my hand on a critical piece of quantum computer, which is Ytterbium, the atoms we use in the Rydberg machine you will hopefully see today. Anyways, let me start with the work. So we decided to do more or less a hands-on overview of 3 technologies. So why this work? What was our motivation here? And so this is obviously like a emerging promising technology, quantum computing, and the research-grade hardware is already there, and it's available to use. We've developed enough, I would say, software infrastructure, and a lot of information is available, but it's, in our experience, for me, for example, as of a few years ago, not too experienced with quantum computing, it was really difficult to read, I would say. So there was a certain gap in like my training as an OR scientist. And so that's why we decided to take OR scientist perspective, and well, we just attempted to pick specific discrete optimization problems and well, investigate the workflow, like what specifically do we need to do to solve a discrete optimization problem. So to be precise, we took 3 well-known problems. It's a T-spin, max independent set, and max cut. And we tried to apply 3 pretty different technologies for that would be seemingly good fit to these problems. So that was Rydberg neutral atoms machine from QEra, quantum annealer from D-Wave, and the quantum approximate optimization algorithm as run on IBM hardware. So that was our setup. And we wanted to sort of try the out-of-the-box experience. So what will happen if we do not go too deep and do not do too much of a fine-tuning? Just what can we achieve? Sort of, if you take Groby, you can just throw it at a problem and it works. So what would be the quantum counterpart of it? And we tried to put a somehow unified workflow to describe these three pretty different technologies in similar terms. Okay, so we I would say identified three computational, like three steps in the workflow, three really high-level steps. So this is modeling, when you take your optimization problem and you represent it in a way that would be suitable for a quantum computer. In our case, it was either QUBO or unit disk max-independent set instance. Then you configure the algorithm, which means that you configure the classical host, the classical part of the algorithm, and the quantum part. And then we will actually run the solution in quantum hardware. So in our case, that was three different machines. And so let's look into that. Let me say a few words, like in general, about these three technologies, and maybe I'll try to somehow describe them in as similar terms as possible. Let's see if it works. So first of all, like if we do the classic approach, so I want to sort of contrast the classical optimization with quantum optimization. I steal these slides from Anita usually. So when we solve the classical optimization problem like we see here, so it's an objective function, we start from some point, and then we do some computational magic, and then we go to another point. And then we take another one, and hopefully we go down. Not every time, so here we went slightly up. But hopefully we end up in a lowest possible point, the true minimum, by traversing different parts of the optimization landscape. Quite often, in quantum optimization, we do sort of the opposite. So we take so this idea of adiabatic, or maybe I should better say annealing-like technologies. When we take a really simple optimization landscape, so we're trying to minimize this very simple function, we just know the answer, and we start from the minimum energy state. And then we deform the energy landscape, the objective function. It looks something like this. And there is a theorem that says under certain conditions, we kind of stay in the optimum of this new system. So the optimal solution changes. So it was here, and now it moved further left, and the objective value changed, but we stayed in the optimum of a new function, right? And then we make it more complicated, and so on and so forth. This is basically implemented quite literally like that in D-Waves machines, the annealing type of machine. So this is, since we've heard that kind of talks a couple of times already in the conference, so this is what happens. I made a quick computational illustration for that. So we start, so along the vertical axis, we have energy levels for the system, and along the horizontal axis, we have normalized time. And so if it's maybe some simple system, maybe it's a 2-qubit system, it has discrete energy levels, right? So we have 4 energy levels, and if we are in so-called adiabatic regime, or sort of adiabatic regime, if we start from a minimum energy state, which means that we are sort of starting in the lowest point on the left figure, we evolve the system, we change the Hamiltonian describing the system, and we sort of stay on that minimum energy state. I mean, instantaneous minimum energy state changes, but we sit on this minimum energy state, which is indicated by this yellow fat line. So we sort of stay there. And then we, when time equals 1, normalized time equals 1, the system completely changed. So it reflects our optimization problem now. And we are in the minimum energy state. So if we measure, we get an optimal solution. That's the idea. However, it's not always the case, and sometimes we have less nice systems, and this is non-adiabatic regime is represented on the right figure here. And the idea, if the energy levels come too close to each other, we start maybe with a minimum energy state, like it's marked, the left part is of the bottom line is yellow, right? But then we start to, like physicists say, we start to get excitations. So we have some probability to end up on the higher energy levels. And if I measure in the end, maybe I'll have some probability to get suboptimal solutions, right? So that's the idea of adiabatic changes. And so this is what implemented in, for example, in D-Wave. So probably I would guess that's the right one. That's not the only device that does that kind of computing. So another one, maybe more interesting, not necessarily way more relevant, but more interesting probably to think about, is that Rydberg machine. So we will see an example of that machine today. So when you have one qubit represented by a single atom. right? And this atom can be in one of the two possible states. It can be a 0, so ground state of the atom, of a single atom, and it can be excited, and that would be like 1 for that atom. And they possess certain properties, and specifically, if two atoms are placed really, really close to each other, one of them can be excited and the other one not. And this is fine, but this situation is, we can make it sort of forbidden, which is a way to say that the energy of that arrangement would be very high and the probability to get there would be very low. So for simplicity, we can think that it's forbidden. And that gives us a native way to solve max-independent set, basically. So we start, initially we arrange the system, we can move the single atoms along the, like geometrically along the 2D grid, and then we place some atoms close, some atoms far apart from each other, and then we shine the laser on that system. And the idea is the interactions between the laser field and the atoms are done in a way that the minimum energy state of the final system would be as many atoms excited as possible, while they still respect that Rydberg constraint that no two atoms that are close enough are excited at the same time. So, I mean, these two annealing-like protocols, the D-waves and the neutral atoms one, look very different on paper. And that was like one of our problems, I guess, when we started looking into that. So these are Hamiltonians for both, right? The top one is from, I guess, more or less from D-Wave's website up to constant multiples, I think. And the bottom one is from QR website. But if you look closely enough, you will see that they are, in fact, pretty similar. So these are indeed very similar protocols. So the first term on the top, a sum of xj's, right? So what does xj gate do? It takes a 1 and it makes it a 0, and it takes a 0, makes it a 1, right? And this is exactly what is happening in the first term in the bottom Hamiltonian for Rydberg machine, right? So this is a sum of x gates as well, in principle. And then in D-Wave's machine, again, the top section, second line, you have linear z terms plus zz terms, right? And this is very similar in the bottom line. So they do in fact resemble each other. It's not the same thing, but they do resemble each other even on that level. And if you remember, yesterday we had a talk from Pascal, and what they were doing, they were exactly sort of matching this Hij coefficients. So they were changing the distances xk, xj in a way so that sort of to match the h coefficients, right? So that was their idea. Sometimes you can sort of do that heuristically, right? So to solve the Kubo icing problem with the second type of device. So well, I guess what I'm trying to highlight here is that these are similar types of protocols, and you can even try to make one simulate the other one. The third approach we tried was a quantum approximate optimization algorithm, which is a slightly different idea, and usually it is introduced well as follows. So we have, again, we start with this adiabatic idea. So we start from initial system in some state that's easy to prepare, described by some easy Hamiltonian, right? And then we have a final state, final system, which will reflect our optimization problem, and we want to find the minimum energy state for the second configuration, for the second Hamiltonian, right? And what we would do with an annealer, we would do like slow change operator. We change the Hamiltonian from a simple to a complicated one, right? So that's the idea. Instead of, and that would be a diabatic approach to that. So instead, we could discretize that. And instead of the continuous slow change operator, we could try to do something like this, right? So if you recall, that machinery is called Trotter expansion, which we apply twice in different places. And we can actually, instead of doing continuous change in the Hamiltonian, time-dependent Hamiltonian, we apply constant Hamiltonians in an interleaved fashion. And in limit, if we have very many of those, of such like discrete applications of two constant Hamiltonians, we end up with the same state. And the idea of QAOA is usually introduced like that. So we say, okay, so what if we just take finite number of those steps? But we allow for, like, I evolve with mixing with a simpler Hamiltonian with the initial Hamiltonian first, but for some finite number, some finite amount of time, and then some problem Hamiltonian, then mixing, and so on and so forth. Yeah, and so how do we know these time periods during which I evolve my system with my mixing and problem Hamiltonians? Well, I just wrap everything into an external classical optimization loop. Right? I guess that's the way it's usually introduced. I sort of have problems with that exposition because I think it's not really obvious why would that work, and I think there might be ways to see it from different perspective. For example, if you take mixer Hamiltonian, the evolution with the mixer Hamiltonian in QAOA, it would do something like this. So every graph here is comprises so a node is a solution to a QBall, and the size of the bubble is the probability to get that solution after a measurement. Okay. And so the top left situation is just I start with a single computational basis state, so 0, 0, 0. And then I apply evolution under mixing Hamiltonian for different betas for different effective times, right? And this is what happens. So if you think about that, so as I increase the beta, it smears the probability outside of that single state. And yeah, there is some point when I sort of achieve close to uniform superposition, and then I just go push the probabilities further away. And I think you can describe problem interaction between mixing and problem Hamiltonian in these terms as well, and you will see that it sort of improves for small enough angles. It sort of improves the solution. When I apply problem Hamiltonian evolution, then mixing Hamiltonian evolution, it improves the solutions if the angles are small enough. I think we can prove that, but maybe that's a glimpse into further research now. But let me maybe go back to the paper. And so we took these three technologies, and they indeed can be described on a higher level in similar terms, right? So we have a modeling step, we have a configuration step, and we have like solution and processing. And so if you look at neutral atoms-based machines, we model a problem. We in that setting that I'm describing, we convert it to unidisc max-independent set problem. We arrange the atoms within the device, like actually using optical tweezers. We arrange the atoms on a position that reflects our graph. And then we do that multiple times to obtain a series of shots, measure, and then we have candidate solutions. Quantum annealer from like D-wave type of machine would look very similarly, except it usually takes QBall as inputs. But the configuration step now includes the embedding of different sorts, right? So we need to the interactions between the variables are subject to, they need to resemble certain device graph, right? Like Chimera or Pegasus in case of D-wave. But then the process is very similar conceptually. We repeat it multiple times, get multiple shots, measure, and have candidate solutions. For QAOA, it is again pretty similar, but we have a outer optimization loop around the shots, right? So we model the problem as a QBall again. We do need to make certain decisions regarding the ansatz, regarding the circuits, the parameterized circuits we use. But then during the solution phase, we still prepare the initial state, run the circuit, and measure, and we repeat it multiple times. And then we have like estimate how good our parameters are, and then we update the parameters, and then we do that multiple times. Hopefully, it gives us better solution than that we started with. And why does it do that intuitively? Well, I guess that was on the previous slide with the graphs. Does not always work like that in practice, and I'll show numbers in a second. We tried to look into sort of issues regarding these technologies, like for each of these high-level steps, right? So there are non-trivial decisions to make everywhere. So in terms of formulation, so necessary number of qubits, for example, obviously depends on the formulation. Depending on which approach, like quantum approach, do I choose, I will need different number of qubits as well. So this is also not independent solution. Then in the device setup, we have algorithm parameters, obviously, and usually there is some sort of classical optimization problem involved when I need to configure my device to run my optimization problem. So for D-wave, that would be embedding. For neutral atoms machine, that would also be some sort of modeling. It's either I embed it as a max-independent set, unit-disk max-independent set, or I try to mimic my QUBO with the items distances like we have seen yesterday with Pascal and so on and so forth. Well, and finally, the solution, there is also a whole spectrum of things to care about during the solution phase. There's pre-processing and post-processing that you, in principle, can do to improve the solutions as well. We deliberately did not look into that because the fine-tuning is, well, infinite, but the things that we could try to improve that. Well, in general, I think it's more or less like with every heuristic, I guess, many knobs to turn. So first, speaking about formulations, again, obviously, even number of qubits, so that such a basic parameter depends on the formulation. We gave the example of TSP, traveling salesman problem, when, like, depending on the formulation we choose, so there might be usual formulations like MTZ, for example, for operations research literature that involves integer variables and that involves inequality constraints that does require quite a few qubits, and to solve it on a quantum machine, it might be more reasonable to take actually quadratic formulation, native quadratic formulation for a TSP, the so-called quadratic assignment problem formulation. And that would require like orders of magnitude fewer qubits. So the point is that formulating the problem for a quantum machine might be different as formulating the problem to be solved with Groby. So it's not necessarily straightforward conversion from a mixed integer program to a QUBO. Then the choice of technology matters mostly because of this setup phase. When we, for example, we take arbitrary QUBO and we want to embed it into device graph for a quantum annealer, like we square the number, or we even worse, the number of qubits we need significantly increases. So if I have a QUBO with a certain number of variables, depending on which technology, which device do I want to land it on, I will need different numbers of qubits because, well, embedding might be different, right? So that's the point. So we tried that, and so we wanted to sort of report the default user experience. Let me put it this way. And so we picked 3 types of problems. That's a synthetic data set. And in the columns, I have here different problems. So unit disk max independent set, max cut, and TSP. And in rows, I have different technologies, which are top to bottom: neutral atoms computer, the annealer, the D-Wave, and then QAOA with IBM, and then the simulated QAOA on a classical machine. And the height of the bar is the number of instances I was able to solve here. And the numbers along the horizontal axis are instance sizes. So for example, we see that for quantum annealer, for max cuts, I was able to solve pretty wide spectrum of problem instances from like 5 nodes to 100-something nodes. However, I had real problems with solving the instances with QAOA, where I was able to solve only very small instances. So my point is the out-of-the-box experience is pretty different. I think we could continue working. We could fine-tune the QAOA and maybe solve more, but that sort of requires more work. That's what I'm trying to say. And for neutral atoms, okay, we were able to solve a spectrum of unit disk max independent set problems, but we were not able to solve reasonably sized max cuts or TSPs because embedding them into max independent set would require more qubits than we had in the machine. The machine we had access to had 256 qubits. And these instances we tried to solve were different. So this figure, like very briefly, I think we're out of time. We had different density of QUBO matrices. So some problems were dense, as in many non-zero entries in the QUBO matrix, and some problems were very sparse, and then we have only a few non-zeros. And interestingly, also with respect to that, for different problems, that embedding, so that device configuration step was drastically different. For example, for max cuts, embedding the problem to start solving it on a quantum annealer. So, okay, let me put it this way. These figures show runtimes that we needed to solve each instance. So 1 bar is 1 instance. How many seconds did it take? And you see that the yellow part of the bar is like quantum time, the annealing time. And the purple, the dark part of the bar, is how much time did it take to embed the problem, so to configure the device to solve the problem. And we see, like, for large max-cut instances, densely connected, we spent most of our time actually trying to land the problem onto the quantum device. So the embedding problem is a hard classical optimization problem. Yeah. Yeah, maybe so we illustrated the fact that number of qubits theoretically depends on the embedding process. Practically, there is no way around it. It's still, if I, for example, embed for a D wave, I probably need like quadratic number of qubits. That's what this figure is about. And now the question is like, well, how good the solutions are. And so bottom line is, in the given time frame, Groby solved most of the problems to optimality and solved them faster than our quantum machinery. We have this a subset of instances which are large max-cut instances where we think that we solved. So Groby was slower and not always found a true optimum in the given time frame, in the given timeout. And however, going back to what Frank Philipson talked about yesterday, so Groby is an exact method and D-wave is a heuristic. And so we compared it to a natural heuristic made out of Groby when we put a timeout on it. And so usually what happens is what you see on the left figure, right? We have a large gap and then it goes down and it finds good solutions relatively early, and then we can just cut the process, and that not necessarily optimal, but we would have a good solutions earlier. And yeah, essentially, I guess more or less our outcome is that for larger instances, it's sort of comparable to Groby, not always better, even for like complicated instances. So we did not really see quantum advantage immediately somehow. Okay, I see we're out of time. Once again, so we try to take an OR view on quantum optimization to see sort of out-of-the-box experience, and we looked into common issues, which is importance of formulations, qubit requirements, and the embedding problems, which we dealt most of the time, I guess, with. Yeah, and for the further research, I would be personally most interested to look into the developments of QAOA and the related methods, and yeah, maybe into applications. If you have time for questions, very welcome. You could also catch me afterwards.
So firstly, like, since you've shown only maximum independence for Rydberg adults.
Yes.
So like, to solve any problem, do you need to do like a polynomial reduction of the other problems?
No, not necessarily. So in our case, sort of yes, because that's the workflow we considered. But yesterday there was a talk about alternative approach to that, right? So you can try to mimic QUBO by changing the atoms distances heuristically, right? But it's probably it's not even approximation; it's also a heuristic. It's right. The guys say that it's not. You cannot do that exactly. So.
And because it's like miss is like the native thing.
Right. Our idea was that if you do a polynomial reduction, like you suggest, that you do have it like solved naturally. So the machine sort of solves the max independence set natively. Yeah, that was. Yes.